Hello everybody, getting ready to do lesson 7.6 part 1, pre-calculus math today, classwork lesson today. My email is animatedpowerpointmathvideo@aol.com. And today's lesson 7.6, the inverse of a square matrix, linear systems and matrices, part 1 here. You got 10 points here for your notebook, and you have 46 points here that will go on your classwork sheet. And for today's lesson, students and teachers, we start out with a bell work. Solve the equation algebraically. Round your result to 3 decimal places. So we have this one and this one. Teachers, give your students about 5-6 minutes to solve these. Pause your video or pause your PowerPoint. See you in 5. Okay, welcome back everybody for your solutions. To 73 here, we can factor this back into e to the x plus 5, e to the x minus 3, and we come to equal 0 here. We use our 0 factoring to find our solution. So 0 would equal e to the x would equal 3 in that case for this one here. So if e to the x equals 3, you got a solution. And then x equals natural log 3 equals 1.099 would be a solution up here to this one. And then down here, when we factor this back, we can get e to the x minus 6 and e to the x minus 4 will equal 0. So in this case here, e to the x can equal 6. And then when we solve for x, we get natural log x equals natural log 6, which will equal 1.792, and then e to the x can also equal 4, and then natural log 4, x equals natural log 4, which equals 1.386. So there are your solutions for today's bell. On into our lesson today, the inverse of a matrix. This section further develops the algebra of matrices. To begin, consider the real number equation, ax equals b. To solve this equation for x, multiply each side of the equation by the inverse of a, provided that a does not equal 0. So when we do that, a to the x, or rather ax equals b, and then the inverse of a times x equals the inverse of a times b. Our a goes away, then we have x equals the inverse of a multiplied times b. That's the side of for solving something algebraically. Knowing that, we can transfer that over into a multiplicative inverse of a, because a to the negative 1 times a equals 1. The definition of multiplicative inverse of a matrix is similar. Definition of the inverse of a square matrix: let A be an n times n matrix, and let I to the n be the n times n identity matrix. If there exists a matrix A to the negative 1 such that A times A to the negative 1 equals I to the nth equals A to the negative 1a. Then A to the negative 1 is called the inverse of A. The symbol a to the negative 1 is read a inverse. So a to the negative 1 would be the same thing as reading it a inverse. Let's try an example now with that concept. The inverse of a matrix. Show that B is the inverse of A, where A equals this matrix and B equals this matrix there. So to show that B is the inverse of A, show that AB equals 1 equals BA as follows. So AB, here's our product here, equals this matrix here, which reduces down to 1, 0, 0, 1. So we do get we have a diagonal here of 1s. And then BA, we just move this over here and this over here. And then we get this same situation here where we have a inverse, or rather an identity matrix here as well when we change our multiplication around like that. As you can see, AB equals I equals BA. This is an example of a square matrix that has an inverse. Note that not all square matrices have inverses. Okay, so let's try one here. Show that B is the inverse of A. We're going to show that this is the inverse of that. So the way we're going to do that, we multiply these two together, and we do get this. We do get our inverse matrix here when we multiply these two together. And then BA, again, when we change the order of our product here, we get the same thing here. So by reversing our order here, multiplication, and both of them come out with an identity matrix like that, that means that B is the inverse of A. Okay, so moving right along here, recall that it is not always true that AB equals BA, even when both products are defined. However, if A and B are both square matrices and AB equals I to the n, then it can be shown that BA equals I to the n. So in example 1, you need only check that AB equals I to the subscript 2. So finding inverse matrices, when a matrix A has an inverse, A is called invertible or non-singular. Otherwise, A is called singular. If it doesn't have an inverse, it's called singular. A non-square matrix cannot have an inverse. So a non-square matrix cannot have an inverse. To see that, if A is of dimension m times n, and B is a dimension n times n, where m cannot equal n, then the products AB and BA are of different dimensions and so cannot be equal to each other. So here is a big note here, students. Take note of that. Not all square matrices have inverses, as you will see later in this section. When a matrix does have an inverse, however, that inverse is unique. Example 2 shows how to use systems of equations to find the inverse of a matrix. So let's go into an example 2 here. Finding the inverse of a matrix, find the inverse of A, which is this here. So how do we find that? To find the inverse of A, try to solve the matrix equation. AX equals I for X. So if we have a 1, 4, -1, -3, and therefore we have x1, 1. This is position 1, 1 here, and then 2, 1 here, then 2, 2, and 1, 2. This is what we need as an inverse for our I here. We need to move this to this over here. So to do that, we have x1, 1 for here, plus 4x2, 1, and then we have negative x1, 1, minus 3x2, 1 here. And then we have x12 plus 4x22 minus x12 minus 3x22 here for that one. So this is A here, this is x, and then this is I over here. So we need to find an x here that will turn this into this from here to here. That's what our x needs to be. So to find that, to find our x, equating corresponding entries, you obtain the following two systems of linear equations. So linear system with variables x11 and x21, x11 and then x21 here, 21 and 11 here. And then x12 plus 4x22 equals 0, 1 here for these two. So linear system with two variables x12 and x22. So the first system using elementary row operations to determine that x11 equals -3. So x11 equals -3 and x21 will equal 1 and x21 here will equal 1. So how do we do that? From the second system, you can determine that x12 equals -4 and x22 equals 1. Therefore, the inverse of A is the inverse A equals x, which will equal -3, -4, and then 1 and 1. That would be your inverse there, drawn from this here. This is 1, 2, row 1, column 2 will be -4, and then row 2, column 2 will be 1. You can use matrix multiplication to check this result. So A times inverse A equals 1, 4, -1, -3. Multiply this by -3, -4, and then 1 and 1. And when you multiply these two together, we will get 1, 0, and 0, 1 for that. And then inverse of A times A, we can now switch our the order of our multiplication here. And then this here, by the way, students, this is 1, 4, and this will be -1, -3. Sorry about this thing being in the way. But anyway, it does come out, it does check. So this does check here as being the inverse of A. So let's try one here. Find the inverse of the matrix if it exists. We need to find the inverse of that. And you need to find the inverse of that, students. So we're going to do work on this one now. So for this one here, A, we're going to put this in augmented matrix. So we have A, therefore I, will equal 2, 0, 0, 3. And we want to get to this point here with our matrix. So to do that, we're going to go 1/2 row 1. So we have 1/2 here. This becomes 1. And then 1/3 row 2. And then this will have our inverse here. Will equal our inverse of A. So the inverse of A would be 1/2, 0, and then 0, 1/3. And then we can pull this out. We can pull these fractionated parts of our matrix out by multiplying through by 1/6. And then this will become 3/6 will be 1/2. And then 2 over 1/6. Or rather 2 times 1/6 will be 1/3. So here is our inverse matrix for this matrix there. In example 2, note that the two systems of linear equations have the same coefficient matrix A. Rather than solve the two systems represented by this and this, 1, 4, 1, 0, and -1, -3, and then we have a 0 and 1 here. Separately, you can solve them simultaneously by adjoining the identity matrix to the coefficient matrix to obtain this situation here. Here's A and I. We have this, therefore we will have that. This doubly augmented matrix can be represented as A, therefore I. By applying Gauss-Jordan elimination to this matrix, you can solve both systems with a elimination process. So how would we go about that? So we have 1, 4, -1, -3, therefore our identity matrix over there. So row 1 plus row 2 here will give us our 0 here. And then this will change our identity over here. And then -4 times row 2 plus row 1. And then this will get rid of this 4 here. And then now we'll have our identity pattern here. And then this matrix over here will be -3, -4 over 1 and 1. So from the doubly augmented matrix A, therefore I, you obtain the matrix I, therefore inverse of A. And so therefore A, or A, therefore I, will go to our I here, our identity matrix, therefore our original, our inverse that we're after here. By going through this process here, we will find our inverse here. This procedural algorithm works for any square matrix that has inverse. So that will work for anything that has an inverse. Find an inverse matrix. Let A be a square matrix of dimension n times n. So to find it, rule number 1, write the n times 2n matrix that consists of the given matrix A on the left and the n times n identity matrix on the right to obtain A, therefore I. 2, if possible, now reduce A to I using elementary row operations on the entire matrix A given I, or A therefore I. The result will be the matrix I therefore inverse A. If this is not possible, then A is not invertible. 3, check your work by multiplying to see that A times inverse A equals I, which would equal A inverse, or rather inverse A times A. Same thing. This multiplication here would be commutative in that respect. Okay, so let's try one. Find the inverse of a matrix. Find the inverse of this matrix here. So begin by adjoining the identity matrix 2A to form the matrix. Here's our identity matrix here. And then this is our original matrix here, down here, A therefore I. Use elementary row operations to obtain I therefore inverse A as follows. So here we want to get to this point here, which we did, and by our row manipulations, this matrix here turned into this matrix here after our row operations. Use elementary row operations to obtain the form I therefore inverse A as follows. So here is our transformation of our identity matrix after we turned our A into an identity matrix. Once we have that, the inverse of A equals this. So this is our inverse of A right here now. Confirm this result by multiplying A by inverse A to obtain I as follows. And then here's your check. So when you multiply this by this, you'll go back to your original matrix there. So this times this will become that. Okay, let's try one. Find the inverse of the matrix if it exists. So here's our matrix there. So A therefore I will equal this here. This is our matrix here, and then we want to get to that point. And then for this to get to that point here, we first out -3 row 1 plus row 2, and then we get this far here. This will become this down here, and then -3 times row 1 plus row 3, and then we'll have this situation here. We got the ones situated there. We came from here to here so far. And then when we continue to do row operations here, we go 1/2 row 2 plus row 1, and we come up with this here is what we have. And then 1/2 row 2, and then we get to this here. And then -3 times row 2 plus row 3. So now we got our 1 back over here. This is changing here. And then we continue here with these row operations here. Now we have this here, and then this is becoming more of our inverse of our original A. This is inverse A, and then our A is turned into an identity matrix. So therefore we have identity, therefore the inverse of A. So here's our identity, and then here is our inverse of A there. So 1, 2, and 2. So the inverse of A is this matrix right here, as designated by that. And that is your 7.6 part 1 classwork lesson. If you need solution PowerPoints, homework sheets, classwork sheets, note-taking guides, email me here, animatedpowerpointmathvideo@aol.com. Thank you very much.